All right, our next speaker is one of our submitted abstracts. Zhou from Apple will be presenting Learning to Route with Confidence Tokens. Thank you.
Okay, hi, can everyone hear me all right? Okay, cool. Hi everyone, my name is Helen, and I'll be presenting our work on learning to route with confidence tokens. This was work done as part of a summer internship led by Alan Trong, who's from Rice University, as well as in collaboration with the rest of our team here at Apple. Pratusha Sarma, John Basio, Oliver Ruiz, and Sarah Baluki as well. So the motivation for our work is that as LLMs are increasingly deployed in real-world applications, it becomes vital to know when they are uncertain about their answers. So these can range from applications in education, to healthcare, to mobile devices, to software workflows. And if one's LLM produces an untrustworthy answer, one might like to be able to fall back to some behavior so that the system overall behaves in a nice way. For example, one might want to route to a larger, perhaps more costly LLM, perhaps monetarily costly due to API access, or time costly in terms of latency. Another thing that one could do is learn to just abstain from answering. So if the LLM is not confident in its answer, then it can say, sorry, I can't help with that, and maybe you could have the system default to some safe behavior. And so the main question of our work is how can we obtain reliable estimates of an LLM's confidence in its answers? So in this work, we introduce self-ref, or self-reflection, a lightweight fine-tuning strategy for teaching LLMs when they should be confident in their predictions. And then we introduce the LLM routing setting, as well as the LLM rejection setting. And we demonstrate that self-reflection outperforms existing approaches in both of these downstream settings. So to give a high-level bird's-eye view of the self-reflection framework, there's a first step, pre-processing, where we augment the data. And then the second step, in training, we do self-reflection fine-tuning. And then the third step, we extract confidence scores. So diving into the first step, in data augmentation, given a base large language model, we use that model to make predictions on all of the training examples. Then, for all the examples that it got incorrect, then we annotate with a unconfidence token, UN. And then for all of the ground truth answers, we annotate those with confidence tokens, CN. And then we mix this data, the unconfident and confident samples, to form an augmented training set. After you have this augmented data, you then proceed with self-reflection fine-tuning. And so this is a parameter-efficient fine-tuning. In our case, we use low-rank adaptation, or LoRa. And then for the confidence tokens, we have trainable embeddings for them, and these are special tokens. So you learn the representation as you're training. And then in order to prevent the model from learning incorrect answers from those incorrect samples, we mask out the gradients from those incorrect answers. And so overall, this fine-tuning procedure encourages the model to increase the probability of confidence tokens given a correct answer. It increases the probability of the unconfident token given incorrect answer. And then finally, we also want to increase the probability of the correct prediction in the first place. And then once we have this fine-tuned trained model, we can proceed with the extraction of the confidence scores. So basically what we do is we take the logits, or the probabilities of the confidence tokens after the model has made its prediction, and then we normalize the probability of the confidence token by the sum of the probability of the confident and unconfident tokens. So this is an example of this whole framework. So given a query, for example, what is the capital of the United States? You pass it through an LLM. Let's say it says Washington, D.C., and it's correct. But let's say you have another query, where's Wakanda? And the LLM says Houston, Texas, and that's incorrect. So given all these predictions from the LLM, you then can create this augmented data set where in the first example, since it was correct, you annotate it with a confidence token. And then in the second example, since it was incorrect, you annotate it with an unconfidence token. And then you fine-tune the LLM with this augmented data set, noting that for Houston, Texas, that answer we would mask out the gradient so that it doesn't learn the incorrect answer. And then once you have these predictions at inference time, once you make a prediction, you look at the probability of the confidence tokens, normalize it, and then extract your confidence score. So given this confidence score, how do we assess its utility? So remember at the start of this talk, I was talking about routing and perhaps some safe fallback mechanism. So let's walk through an example. Let's say you have a user query, and then you pass it through a small fine-tuned language model that you have controlled and trained using this self-reflection technique. It outputs an answer. It outputs whether it's confident. If it's confident, then you can go ahead and already just output that answer. But if it's not confident, then we want to route it. And so if we route this unconfident answer, there are two options here. The first is that we can route to a larger language model, and perhaps you have API access to this larger language model, and then you can take its response there. And then the second option is you can reject or abstain and fall back to some default behavior. For example, like, sorry, I'm not sure about that. And so for these two downstream tasks, routing and rejection learning, we have a couple experiment setups. And so first of all, we fine-tune two language models using self-reflection. The first is Llama 3 8B instruct, and then Mistral 7B instruct. For the purpose of this talk, I'll just talk about MMLU results, but we've also explored other data sets as well. But MMLU consists of around 16,000 samples across 57 academic subjects, and it's a multiple choice data set. And then for the routing task, based on the confidence score, we route to a larger language model, Llama 7DB instruct. And then for the rejection learning task, what we do is in the data set, we delete the ground truth in 50% of the examples so that now the actual answer is none of the above. And then when the model outputs a confidence score, if it's not confident in its answers, then it can choose to abstain from answering. We benchmark our method against a couple of other baselines that are prevalent in the literature. The first is verbalizing the confidence. So first you can ask the LLM to make its prediction, but then also say, how confident are you? Rate your answer from 0 to 1. And then so you can extract this decimal representation directly from the output of the LLM. The second baseline that we compare against is extracting from the token probabilities. So when the LLM makes a prediction, you look at the token probabilities of that prediction to obtain your score. And then the final one is the self-reflection technique, where we extract the confidence scores based on the confidence tokens. So here are results on the routing setting. So how you read this plot, the y-axis is the overall system accuracy. So how many would you have gotten right if you had chosen to route at different rates? And the rate is the x-axis. So on the leftmost side of the plot, the 0, that's basically how the small LLM would do on its own without routing at all. And then on the right side of the plot, that's what if you 100% routed to this larger model. And so the black solid line gives a random routing baseline. So if you just randomly route like 50% of the samples, then you would obtain a particular accuracy. And then we also look at what if you route based on different thresholds of these confidence scores from both our method, the self-reflection methods, as well as looking at the verbalized uncertainties as well as the token probabilities. And so in these plots, you can see that the blue and the orange for the self-reflection lines, those outperform all these other uncertainty metrics or measures. And we can also see, interestingly, that even if you don't route 100%, you can actually obtain equivalent or even slightly better performance to routing 100%. So you can gain both, you can have gains both in terms of latency as well as accuracy from this technique. And so for Llama, we were able to see slightly larger gains, and then for Mistral, it was still performing the best compared to other techniques. However, maybe the gains were not as large. For the rejection learning setting, so this is where the ground truth answer is like none of the above sometimes. And we look at the precision and recall of the rejection option. So for the precision, it's like what is the precision of choosing the rejection option? And again, we can see that in these precision recall curves, the self-reflection approach outperforms these other baselines, verbalizing and looking at the probabilities. So in addition to these downstream tasks, things that people might care about in terms of uncertainty metrics is expected calibration error and Breyer score. And so we also look at basically how close the predicted probability is to the true probability of correctness in both models and then across all these different baselines. So we know that the self-reflection technique did achieve the best expected calibration error for the Llama model, but it only achieved the second best in terms of Breyer score. And then for the Mistral model, it didn't achieve the best for expected calibration error, but it achieved the second best for Breyer score. So one thing that we can take away from this is that calibration metrics may not perfectly align with the downstream utility of these scores. And so in conclusion, the self-reflection approach is a lightweight training strategy that teaches LLMs when to be confident. We have these estimates that are tied directly to the correctness of the model, and it's customized to the base model, and then the generated answer is like taken into account when you compute these confidence scores. And then we also demonstrate that self-reflection outperforms baselines on confidence-based routing and rejection learning. And even without task-specific fine-tuning, self-reflection can be used for learning to reject quite effectively, and routing, it can outperform even just routing to the larger model 100% of the time. And in future work, we'd also be exploring more data sets and also perhaps more complex outputs. So here I've just presented multiple choice, but one can think about how you might be able to annotate more complex outputs if you have a longer form free text, things like that. So yeah, thank you all for your time, and happy to take questions.
Thanks for the talk. I have one question about the definition of confidence. So it seems to me like the token is more correlated to the correctness instead of like how confident the answer is. Can you explain to me like what do you think if we really want to evaluate how, like even if the model is incorrect, it can be highly confident. So I'm trying to understand what's your thought about that.
Right. So if the model is incorrect but it's highly confident, that is something that we do see in these baseline approaches. Yeah. But the way that we train the model, we explicitly tie confidence to correctness. And so this would help mitigate that a little bit. There's also sort of this notion of uncertainty that's sort of the inherent uncertainty of a question, and then there's like the baseline uncertainty versus the model's uncertainty in it. And so I think that this approach maybe would focus a little more on the model's uncertainty. Yeah.
Okay, thank you.
Mm-hmm. We can do one more question.
Hello. I have a question about technical aspect of this confidence token and non-confidence. So are you trying to predict just one out of two tokens, whether it's confident token or not confident, or you are trying to, you have a set of tokens which represent confidence from 0 to 1, like 0.1, 0.2, and you predict one of them. Let's say you have 10 tokens which represent that.
So that would be an interesting thing to explore. But for our task, we've just have two tokens, a confidence and an unconfidence, and then we obtain this continuous score by normalizing the probability of the confident token by the sum of the unconfident and confident. So you can still obtain this continuous representation without necessarily coming up with many different confident tokens. But yeah, I think it could be something interesting to explore. You could even explore other notions of confidence beyond correctness and come up with new tokens for that as well. Yeah.
If there is a paper anywhere where we can read it?
So this is it will be under review very soon. So when it's ready, we'll post it on arXiv.
Thank you.
Yeah, thank you.
All right, let's thank our speaker.